Well, the reason I think this talk can be interesting, even for those who are more into algorithms and machine learning and things, is that, as we will see, we will look at alignment dynamics, and alignment is basically a process which takes place on a manifold, and it's related to the, say, the emergence of statistics on manifolds, which I think can be interesting for data sciences. But here, my original motivation was on collective dynamics, so it's just essentially the emergence phenomena where you have individual rules of interactions between close agents, and these local rules give rise to large-scale patterns which have a scale which is much larger than the individual scales, right? So this is the main interest, and in order to observe the large scale, it's not easy using agent-based models. So one of the key issue is actually coarse graining, how to get from the individual scale to the system scale, and this is the topic of my talk, and more specifically, I'm interested, as I said, in alignment dynamics, and I'm going to actually focus on two kinds of alignment dynamics. One is essentially alignment of directions of motion. So here I'm interested in self-propelled particles like birds, but it can be also, as we will see, some other kinds of particles. And so there's been a model proposed by Vikshek already in 1995, where basically the agents align to the neighbors plus some noise, right? And recently it came to my mind that actually sometimes you would like to align not only the direction of motion but the whole body, so that would be an alignment of a frame rather than alignment just of direction. So I've been interested into the comparison between these two kinds of mechanisms. So why are we interested in aligning frames rather than directions? Okay, we could be interested in the alignments of dolphins, but of course it's limited application, although very interesting probably. But I'm going to give you another example of why we could be interested in this. And this is this movie. Okay, right. So it's actually a sperm sample. So that's ram sperm, so which is observed under the microscope. And what you observe very, very active turbulence of the sperm, which is driven by the motion of the spermatozoa. The question is, what do we see here? And at first glance, you could say, okay, we just observe the density of the sperm. These black areas would be like the higher densities, and the white areas lower densities. But it turns out that ram sperm is extremely concentrated, almost like packing threshold. So there is not that much space for sperm to compress or dilate. And rather another explanation, and we still don't know, but another explanation which has been proposed is that actually what we observe here is the orientation of the sperm. The sperm is flat. It's a kind of a racket. And so according to whether it's this direction or this direction is not going to, say, transmit the light or reflect the light in the same way. And so what we are seeing here is rather orientation waves rather than density waves, right? So, and this is really a full body orientation because the sperm is actually a three-dimensional structure. It's actually not even, so there is a, so it's not just flat. It has a, the bottom is flat and the top is a little bit curved. So it's really, there is also the flagellum beating, which is highly non-symmetric. So this is one of the my main drive into this problem was actually to find a model to match these videos. Actually, the application of this is artificial insemination. So it's AI, but not the same AI as what we do in the Turing Institute. So artificial insemination, these are the things that the people in AI center actually monitor to select the sperm sample to either commercialize them or not, right? So they score them, and according to the score, they are going to keep them or they are going to throw them away, right?
There's also translational motion here.
So this is so essentially you put the drop of sperm on a glass and you observe it from the. So here I think in this experiment we use the cell, so that's basically there is 100 micron depth, and according to I forgot to say that's a collaboration with some fluid mechanics people in Toulouse, and they have measured actually that there is a very little motion in the vertical direction, but it's basically maybe due to the fact that your sample is very flat. Okay, so is it answering your question?
Horizontal direction, there is translation.
So you're seeing from above. So so you have the microscope, you have a glass, and you have and so you're seeing
There is no net motion in the sense that they want to go to the border or something like that.
No, here they are confined, so they just rotate. They just they just move. They have to move because the sperm is a stupid machine. It has it has an energy supply, and it just beats, and it has to move. And so the motion is essentially driven by the confinement. The collective motion is driven by the confinement in the cell, right?
Maybe you will speak about the persistence of the orientation in terms of the translational motion.
Right. So, but the orientation is just right now we don't really have a. So we tried to do experiments, but they were not conclusive about whether we see orientation here or not. This is right now it's a hypothesis. It's not something proven yet. Right. So. Right. So this is the idea. So the first model in which we just align like rods, or it's actually active rods, so they have a polarity, is this model proposed by Vikshak, which is actually quite close to Jose Carrillo's talk yesterday on Cooker's mail. It's kind of a Cooker's mail plus self-propulsion. Here, the self-propulsion is encoded into the fact that the particles have speed 1, uniform. So the velocity is just a vector of norm 1. And we have just displacement is proportional to the velocity. The speed is a. Take it 1 if you like. And the velocity evolves according to the stochastic differential equation. So there is noise with intensity tau. And there is an alignment force. And the alignment force is constructed as follows. So you're taking your test particle xk, you're drawing a circle of radius r around it, you're looking at all the other particles in this circle. These are the velocities vj's, vj of norm 1, then you sum, you get a vector which doesn't necessarily have norm 1, but then you normalize it, right? So this is the vk bar. So that becomes a target velocity for the particle k, and so this term is basically a relaxation of v to this target velocity vk with a rate nu. So nu is basically the rate of change of the velocity according to the alignment interactions with the neighbors, whereas tau is the noise intensity, right? So you have a projection here just to ensure that v stays of norm 1, and in order to this probability to be true, you have actually to interpret this SDE as in the Stratonovich sense. Right, so now let's think of a model for aligning body orientation, right? So essentially, the body orientation is encoded into a rotation that sends a reference frame to the local body frame of the agent. So forget about the cues for a while. So that's encoded into a rotation map. So that sends this frame to this one. So basically the variables attached to the agents are the positions and this rotation. And by convention, we assume that the propulsion direction is the direction of the first arrow. So the direction which maps the first axis vector in the rotation, right? So this axis is mapped into this, and this is the propulsion direction. So the particles move at this velocity. Again, the speed is a. And now what about the alignment? So what we are doing, so first we have a certain noise, right? So we have, say, a Brownian noise in the matrix space, and then we reproject it onto the tangent space to the rotation group at the rotation AK. So that's a standard noise. And how about the alignment? We have, in some sense, to define what's the average body orientation of the neighbors. So one idea is just to take the neighbors J, sum their rotation matrices, and you get a matrix, which is not necessarily a rotation, and sort of normalize it. And the natural way to do that is just to use the polar decomposition. So you know that you can decompose any matrix, non-singular matrix, as A times S, where A is a rotation and S is a symmetric matrix. And yes, and if the determinant of M is positive, then you can take A as a rotation and S as positive diagonal entries. So basically, you reconstruct, you assume that by this operation, you reconstruct a rotation. Of course, there are cases where this is untrue. We are supposing that at least if we start from a sufficiently polarized state, then this is going to restore a rotation matrix, right? So because this is going to become the average body orientation of the neighbors, and that's going to be the target of the alignment, right? So this is basically a kind of a generalization of the previous dynamics, and let me give you some illustration of what they're doing. So the Vic-Shack dynamics is there. Actually, we have this video shows actually a kind of a phase transition that I'm not going to discuss in this talk. These systems exhibit a phase transition in the sense that if you lower the noise just a little bit below a threshold, then instead of having just a random motion, then you form clusters of aligned particles, right? So this is a symmetry breaking transition from a uniform state to polarized state. And this is basically one of the manifestations of collective dynamics, right? But I'm not going to discuss that here. Essentially, I'm interested in these clusters, and if I'm looking at the body orientation dynamics, I get something like this. So the colors actually indicate so imagine that my agent has three sides, like a tetrahedron. So there are sides that are red, blue, and green, and the back is white. So essentially, the same color means the same body orientation. You see that the particles form clusters. These clusters move in the same direction and at the same time has the same body orientation. But different clusters have different body orientations, and when they interact, then there is some kind of mixing, and then after some time, they exit again with a different direction and different body orientations. So when we saw this movie, it was very hard to imagine whether we were doing really something different from the Vic-Shack, right? Because the Vic-Shack, well, we also form these clusters. In some regimes, you have, and actually in lower densities, I should have shown lower densities, you see about the same kind of thing. So the question was, is there a genuine phenomenon that's brought by the body orientation? So for instance, would differences in body orientation in the crowd would drive them to turn, whereas they wouldn't have turned if they would have just taken into account the direction only, right? So this is the thing. And from the particle dynamics, it's not clear what's happening. And so this is also one of the advantages of going to a coarse-grained model is that they are more prone to analysis, and then this kind of question can be more easily answered on macroscopic models. So this is one of the reasons why we wanted to do that. Right, so it turns out that in 3D, at least, when you're dealing with rotations, there is a very convenient algebraic tool, which is the Quaternions. And unfortunately, it doesn't work in more than 3D. So everything what I'm going to say now is only restricted to 3D, because in more than 3D, we don't have the Quaternions. We may have something more complicated that could possibly be used, but it's not done yet.
But your question can be asked in 2 dimensions even, no?
Yeah, so in 2 dimensions, if you assume that the third dimension is always, they are always parallel, then it reduces to the Vic-check. So if you take the third dimension always pointing in the vertical direction, then it's basically a dynamics on the rotation groups of 2 dimensions, but this is the same as the sphere in 2 dimensions. So it's basically the same dynamics. So this is really why we need 3 dimensions, and we need a Quaternion. So just a very a brief recap on the Quaternions. We're not going to use them. I mean, just there is one interesting features about them, and this is why I like to show them. So the Quaternions are essentially like the complex numbers, but imagine that the complex numbers, instead of being 1 dimension, is 3 dimensions, right? So you have the real part, Q0, and then the imaginary part is a vector, Q1, Q2, Q3, which is a 3-dimensional vector, right? So the imaginary part of the Quaternions is essentially like 3-dimensional space. And now you have multiplication rules between 1 ijk, which is written here, that make this structure a division ring. So as I said, you can define the real and the imaginary part. And a conjugate, where you take a minus in front of the imaginary part. So when you multiply P and the conjugate of Q, you get the standard inner product in R4, right? Because 1 dimension of 3 is equal to 4. And so when you have an inner product, you can look at the sphere in R4. So that's the unitary Quaternions, and they, of course, form something that's the 3-sphere, right? But the unitary Quaternions have this property that they can be written in a very nice way, in this way. So you take a number of between 0 and 1, you can write it cosine of theta over 2. And then you take a vector, unit vector in R3, which is now, therefore, an element of the 2-sphere, right? And you multiply by the sine of the same angle as this one. And this forms a unitary Quaternions, right? Because cosine squared, here the norm is 1, plus sine squared is equal to 1. It turns out that by writing this, you encode a rotation of angle theta and rotation axis n, right? And the way you do that is that you take a vector of R3, you consider it as an imaginary Quaternion, and you take this imaginary Quaternion, you multiply on the right by the conjugate of this unitary Quaternion, and on the left by the Quaternion itself. Take that, then you get again an imaginary Quaternion. Okay, you can take the imaginary part. This is a vector of R3, and this is exactly this operation gives you the rotation of V about the axis n with angle theta. And you have theta over 2 here because you see you have 2 copies of Q acting to get the rotation, right? So you have so essentially, you can encode a rotation by a unitary Quaternion. Actually, it's a group homomorphism because you take the product of 2 Quaternions. This gives you the product of the corresponding rotation. It's not an isomorphism because, and this is a problem for us, the unitary Quaternion and its opposite both encode the same rotation, right? Both encode the same rotation. And so using this, we can rewrite our dynamics in terms of the position and a Quaternion, where the propulsion direction is just given by the rotation of E1 by this Quaternion. So this is what we call E1 of QK. So this is going to be the first equation. And we're now writing an equation on R4 for the unitary Quaternion QK, which is again like this. So you have the noise. Okay, you project the noise onto the tangent plane to the 3-sphere at this unitary Quaternion in order to guarantee that the motion is on the 3 sphere. And then the alignment is going to be the alignment of our body frame. So we had the feeling that it would correspond to the alignment of the quaternions, right? But there is a little difficulty because the quaternion and its opposite encode the same rotation. So it cannot be standard alignment because if you have 2 unitary quaternions, you could align them like this, okay, like this. That would be polar alignment, or you could align them like this, which would be called nematic alignment. And clearly, since this guy is the same as the opposite, what you need to take is the nematic alignment, right? So that means that essentially we are facing exactly a framework which has been heavily studied in the liquid crystal community, which is nematic alignment. So how do people proceed in liquid crystals? They form what's called a Q-tensor. So that's basically instead of so it's forming actually. So you have the neighboring agents, J. You're taking their quaternion and you form the tensor product of this quaternion with itself. So this is basically a projection matrix. You sum over the neighboring particles. So then what you get is a symmetric matrix, right? So that's the Q-tensor. Usually you remove the trace, but it's really not important here. So this was called the Degond Q-tensor. And so what you call the mean nematic alignment, so the direction where you want to align, is going to be the leading eigenvector of this symmetric matrix. So the idea is the symmetric matrix gives you some kind of ellipsoid, right? And the axis of the elongation of the ellipsoid is actually giving you the right alignment direction, right? So basically, you're taking this leading eigenvector and you want to align with it, right? So if I did like before, like I put just a relaxation towards qk bar, again, I would have something that's not invariant by change of this qk bar, this mean alignment direction, and minus qk bar. So actually, I have to put something which is quadratic in that guy. And so the idea is just to multiply by this inner product, right? And what this inner product does exactly what we thought is that instead of when you have two vectors like that, it will align like this and not like this, right? It's making the good change of sign that allows you to do the nematic alignment. So you could, so we did that, but sort of kind of randomly, I would say it was the simplest idea that came to our mind. It turns out that this dynamics, when you map it back to the rotation, gives you exactly the same dynamics as before, right? So it's kind of good. We were rather a bit surprised by this because, but it turns out to be true, right? So it turns out that somehow, I remember discussing with a fluid dynamics friend and saying that there were a lot of results which are known about the liquid crystals. Unfortunately, not everything is known. Everything is known in dimension 3, but not in dimension 4. And then he laughed at me because he'd never saw the use of a liquid crystal display in dimension 4. Never found it in the shop. It turns out that liquid crystal in dimension 4 are just body alignment or just rotations, right? So it turns out that alignment of rotation is just alignment of 4-dimensional liquid crystals. And this is also interesting because we started from alignment of rotation matrices, so alignment in the rotation group, and now we are looking at alignment in symmetric matrices. So actually we've mapped rotation matrices to symmetric matrices, which is way simpler because symmetric matrices are a linear space, right? So this is the interest of, unfortunately, there is no such approach for higher dimension than 3, so we're still looking at this in more dimension. So what we do, so basically what we we did is from this system, or the other one, the one by Vicek, coarse-grain them and try to compare them on the coarse-grained equations, right? So I'm going to go a little bit fast on the various steps of the coarse-graining because lack of time, but let me flash the important points. So let me do the coarse-graining on the Quaternion system. So essentially there are two steps. The first one is actually to take the previous dynamics. We take the previous dynamics and we are saying, okay, instead of looking at every particle at every time, let us take one representative particle and try to look at the probability of presence of this particle in the space of positions and quaternions, right? So we are going to actually isolate a particle and looking at the distribution of particles at position x and quaternion q at time t. So if the particles were independent, were not interacting, then it basically would just be an exercise using Ito's formula to get that this probability satisfies this equation. So this is contribution of the drift. So this is the motion in space. This is alignment, and this is noise. However, the fact that the particles are interacting make the exercise a little bit more complicated. And in particular, there is a difficulty in the fact that since we're taking the leading eigenvector of the Q tensor, somehow we have to ensure that this leading eigenvector is unique. Otherwise, we have some some problems. So we have, in some sense, to guarantee that at any time the quaternions stay away from the manifolds where two eigenvalues are equal, right? So this kind of estimate is pretty difficult to obtain, right? So right now we haven't any rigorous results on the mapping from the dynamics to here. However, for the Vicek, and provided you do not do the normalization as here, then there are some theoretical results, notably by José Carrillo. So somehow we have good faith that the result is true, but there are some technicalities to get that. But basically this is it. So the alignment term is as before. You have the projection. So these are the Plas-Beltrami operators or the divergence on the 3-sphere. Here we have the projection to guarantee that this vector is tangent to the sphere. And what it is the same alignment force as before. We try to align to the mean orientation QF bar with this weight. And the mean orientation is the leading eigenvector of the Q tensor, which is now an integral expression. So we integrate over neighboring particles in space and all of the quaternions modeling the orientation of the particles, right? So this is basically just a direct translation of the previous dynamics. This is the mean field model. That's the first step to get there. So you need to go from the particles to get to here rigorously. You need to let n go to infinity because of the interaction of the particles, and you have to control the correlation, and they basically go to 0 when n go to infinity. But once you're there, then there is a second step, the coarse-graining, which basically says, okay, instead of looking to the whole distribution, why don't we just look at the density of the particles and maybe this quantity, which is the mean orientation, right? So this is basically the goal. And this is true in the asymptotic regime where you need to look at large time and space scales. So basically, after some scaling, you're single out this asymptotic problem where the epsilon here stands to for the ratio of the small scale to the large scale. So you want an equation valid to the large scale. So basically the same equation. The thing also that needs to be noticed is that now the Q tensor is not an average over space because we assume that the region over which we average is shrinking to 0 when epsilon goes to 0. Essentially, the averaging region is microscopic. So in the end, the Q tensor is just an average over the quaternions, but localized at position x, right? And so now the goal is to let epsilon go to 0 in this equation. And So let's rewrite the equation like so. So we have on the left-hand side the time and space differential operators, and on the right-hand side everything that acts on the quaternion Q, so the noise and the alignment term. Okay, this parameter K is fixed. It's just the ratio of the alignment intensity nu to the noise tau. So it's a fixed parameter. But you see that it's going to actually trigger or measure the ratio between the alignment and the noise. So the idea is what in the limit epsilon to 0, you find an equilibrium of this, which means that you at any given time, noise and alignment just balance exactly. And somehow their balance is actually measured by this parameter K, so how much the alignment is strong compared to the noise, right? So it turns out that the zeros of this operator can be computed, and they are somehow something similar to what's called von Mises distribution. So it's not exactly this function. This is a true von Mises distribution from Wikipedia. So essentially, this is what you find is the equilibrium are the same type or the same shape, essentially. But they are, so here is the circle, so it's in 2D. Here is a circle from minus pi to pi. Here, because of the square, you would have two bumps between minus pi to pi, right? So basically, it should be, should be considered on minus pi over 2, pi over 2. But essentially, it's the same. So the parameter K here, the larger K, the more peaked the distribution is. So when K is infinity, then it's basically a Dirac delta. And when K is 0, it's basically a uniform distribution. And it's peaked around this quantity Q bar, which is the mean orientation. So Q bar can be anything on the 3-sphere. So you have a manifold of equilibria, which is parameterized by the 3-sphere and which have this shape, right? So now the point is that if now you take your solution of the kinetic equation, so when you do epsilon to 0, well, you converge to an equilibrium of this shape. Well, it has to be weighted by some quantity that gives you the number of particles at this position and time, so that's the rho. And obviously, where the von Mises concentrates, which direction it concentrates to, can be also dependent on space and time. And so the game is actually to find the equations satisfied by these two quantities, right? So my time is soon over. So let me just give you a very brief idea. So you see the problem is you have a singular. So basically you go back to the equation. If you plug this quantity inside here, well, here you have basically a 0 over 0, right? Because this C of f is going to go to 0, epsilon go to 0. So basically, this is a singularity that you need to remove. And the way to remove it is by taking moments. So typically, if you integrate over the quaternions, this guy will go away because you have conservation of mass, and you will get the continuity equation. The difficulty is that to get the other parameters Q bar, normally in gases, for instance, in rarefied gases, you will use a momentum conservation. But here you don't have such momentum conservation. So we have devised a trick, which we call the generalized collision invariant. It turns out that you can still apply this kind of pseudo conservations by multiplying this equation against a specific function, which is not trivial to find. Actually, it's the solution of an elliptic equation that's basically related to the joint of the collision operator. But basically, it's once you can solve it, it's exact. And once you do that, you can multiply. Basically, you can multiply this equation by this function, integrate over Q, and again get rid of this guy. And then you get another equation for Q bar. So that's basically the tricks. And in the end, you get an equation. Okay, so you get an equation which is this one. Let me flash the whole system. So now you have an equation for the density and for the mean body orientation encoded into this quaternion Q bar. All right, so you can say, okay, this is not very enlightening. I have a lot of things. Okay, so let me try to compare with what you get for the simple alignment dynamics for the Vic-Check model. For the Vic-Check model, this is what you would get. So omega would be just the mean direction of motion of the agents. So it would be a unit vector, but essentially you would get a continuity equation for the mass density, and then an equation which is akin to the, say, momentum balance equation in compressible gas dynamics with the, some differences. You see you have the constraint that the direction of the velocity is 1, so you have this projection that guarantees that this is a pressure term. This pressure term will still be orthogonal to omega because this is a derivative of omega. So that's one difference with the rarefied gas dynamics. There is another difference in the fact that these two coefficients might be different. But, and that's a signature actually of a loss of Galilean invariance. But, so this is a rather simple model. We have worked with it quite a lot. It gives a pretty good results in comparison to the particle model. What is now the new model? So the new model is a model for a frame. So let me call omega u and v the three vectors of the frame. The first vector is the same as in the Vic-Check model. So you see basically the first two equations are the equations, the same equation as for the Vic-Check model. Then you have two other equations for the two other vectors of the frame. Actually, you can check that these equations preserve the frame structure. But if we concentrate on these first two equations and compare with the Vic-Check model, you see that we basically have the same equations except for an extra term here, right, which you can write in this way. So the omega u and v are the three vectors of the frame. So it's really taking into account, so we call it R, because it's related, it's like rotational, it's really related to the curl of the axis of rotation of the rotation, encoding the body attitude. So you see that you have this extra term that actually differs from the Vic-Check, and of course u and v have to be computed by the two equations. So in the conclusion, we see that the two dynamics are not identical. You really have a genuine contribution of the body frame into the evolution of the direction of motion of the agents, right? So, well, basically this is it. So the answer to the question I asked at the beginning, are the two dynamics really identical? The answer is no. And we needed to proceed to the coarse graining to be able to answer this question. Right, so there is a summary and perspective. The perspectives are many because essentially we have mostly no information about what this model, how this model behaves mathematically. And the question of the high dimension, so again, I come back to this question because I thought it was just a pure, mathematical question, but then I talked to a data scientist who told me that using this kind of approach to actually analyze structured data, which can be of the form of a rotation matrices, could actually be useful. So this is my sort of connection with this meeting. Thank you very much.